All right, let's talk about the invisible forces all around us. We're going to dive deep into the hidden engineering that literally stops a powerful machine from shaking an entire building apart. Let's get right into it.
I mean, think about it. Look around the building you're in right now. I guarantee you, somewhere in the walls or on the roof, there's a powerful motor spinning, a huge fan turning, or a pump just like this one working away. So, what's stopping all that raw energy from turning your office into one of those giant massage chairs? Well, it's not magic. It's some seriously clever engineering that's hiding in plain sight.
And this is our star for today. Meet our culprit, a 15-horsepower, 100-kilogram pump, spinning away at 2,000 revolutions per minute. Now, this little beast is the heart of a building's HVAC system. But if you don't control it, it's basically just a high-tech shaking machine.
Okay, so let's really frame the problem here. What would actually happen if we just took this thing, bolted it directly to the floor, and flipped the switch? Well, it wouldn't be pretty, that's for sure. All that vibration would travel right through the concrete and steel, creating this low, humming noise that can drive people absolutely crazy. You might even feel the floor physically shaking under your feet, and all that rattling, it just accelerates the wear and tear on the pump itself, on the pipes, on everything connected to it. It's basically a recipe for disaster. Tons of noise complaints and equipment that fails way before it should.
So how do we stop it? I mean, we can't just turn the pump off. The solution is actually, believe it or not, elegantly simple in its concept, and it all comes down to being, well, lazy.
First things first, we have to understand the rhythm of our shaking machine. At 2,000 RPM, it's vibrating back and forth 33.3 times every single second. In engineering terms, that's its forcing frequency. You can think of it as the frantic beat of the machine's own dance.
Now here's where we get clever. We're going to introduce our own rhythm by putting the pump on springs. See, every spring system has what's called a natural frequency. That's the slow, lazy pace it likes to bounce at if you just give it a little push. A great example is your car's suspension gently rocking after you go over a speed bump. That is its natural frequency.
And this right here, this is the secret sauce. To isolate all that vibration, you need a huge mismatch between those two frequencies. You have to pick a spring that is so lazy, so slow to respond, that the pump's crazy 33 times a second dance is just way too fast for it. The pump literally finishes its wiggle before the spring even has a chance to react and pass that energy down into the floor. It just gets absorbed.
Now, for this project, the goal wasn't just to make things a little better. The target, the engineering requirement, was to stop 98% of the pump's vibrational energy from ever reaching the building's structure. That is a really, really high bar to clear.
So how do you even begin to hit a crazy target like 98%? Well, engineers don't just guess. You follow a rulebook, a standard that blends pure physics with decades of real-world experience. The only question is, which rulebook do you pick?
You've basically got two main paths. You could go with a pure physics calculation, that's the analytical design. The thing is, it kind of lives in a perfect world where it assumes the floor is perfectly rigid, which it never is. Or you can use the ASHRAE standard, which is way more practical. It's based on tons of data from thousands of real buildings where, floors actually bend and flex.
And for a job like this, the ASHRAE handbook is the clear winner. It's not even a contest. Why? Well, it has specific rules just for this type of pump, it actually accounts for the building structure, and most importantly, its rules are designed around human comfort. It's all about stopping the specific noises and vibrations that people actually notice and complain about.
So, after consulting the rulebook, we have our magic number. See, ASHRAE doesn't just give you a spring model to buy, it gives you a performance requirement. It says that whatever springs you choose, they must compress, or deflect, by at least 0.75 inches just from the weight of the pump sitting on them. This one single number is now going to drive our entire design.
Okay, with our design rule in hand, we can now move on to the fun part, actually building the system. You can think of it like we're constructing a physical trap to capture all that vibrational energy before it ever has a chance to escape. Now here's a crucial point. We need more than just springs. A 100-kilogram pump is actually pretty light and top-heavy. If we just put it on springs by itself, the kick from that 15-horsepower motor starting up would make it rock and thrash around violently. So what's the solution? We mount the pump onto a massive slab of concrete first. It's called an inertia base, and that adds over 300 kilograms of stabilizing mass and dramatically lowers the center of gravity. Problem solved. The assembly is a really logical sequence.
First, a concrete housekeeping pad is poured right onto the floor. That gives you a perfectly level and rigid surface to work with. Then, the spring isolators get placed on that pad. And finally, that huge concrete inertia base, with the pump already bolted to it, is carefully lowered right onto the springs.
Now it's time to pick the actual springs. The total weight of our pump and base is about 895 pounds, so that's roughly 224 pounds on each of the four corners. So we look at the catalogs from the top manufacturers, like Mason and Kinetics, and you see something really interesting. Their products are almost identical. Both offer a spring rated for 250 pounds that deflects 1.79 inches.
So if the performance numbers are the same, how on earth do you choose? Well, you got to look at the details. The Mason spring won out here because it has a special neoprene pad underneath that stops any high-frequency noise from getting through. It's got a built-in leveling bolt, which is absolutely critical for installation. It has better corrosion protection and a guaranteed stable geometry to prevent tipping. These are the practical, real-world features that separate a good design from a truly great one.
And that brings us to the final, and maybe the most important part of this whole process. You can have the most perfect design on paper, but if you mess up the installation, all of that hard work is for nothing. The number one enemy here is something called short-circuiting. Imagine this. You build a perfect moat around a castle, but then you accidentally leave a single stone bridge going across it. That's a short circuit. If a rigid pipe touches the pump, or even if a piece of trash gets wedged under that concrete base, it creates a direct path, a vibration bridge, that bypasses our springs completely, making them 100% useless.
So, to prevent that nightmare scenario, you follow a very strict checklist. You have to install flexible connectors on all the pipes. You have to make absolutely sure that 1-inch air gap under the base stays perfectly clear of any debris. You use those leveling bolts to ensure each spring is carrying its exact share of the load, and you use restraints so the whole thing doesn't jump up if it gets drained for maintenance.
So, after all of that meticulous work, was the result? Well, the original target was 98% isolation, but by choosing a spring that had a 1.79-inch deflection, which was more than double the minimum we needed, the final design actually achieves over 99% isolation efficiency. The shaking machine has officially been tamed.
And that really makes you wonder, doesn't it? From the massive dampers that stop skyscrapers from swaying in the wind, to the tiny little rubber grommets that silence the fan inside your computer, our world is just filled with this kind of invisible engineering. What other elegant solutions are quietly working all around you right now, keeping your world stable